Our next speaker is Akshat Mudgal from Ohio State, who will talk about additive structure for sets with relatively small doubling.
Awesome. Thank you, Mel, for your introduction and for organizing this very nice conference. Maybe just a quick correction. I'm from Warwick, but this is joint work with Yifan Jing, who's
Oh,
at,
I'm sorry. Yes.
no worries, who's at, Yifan Jing, who's at the Ohio State University. Great. So, I mean, I guess as is the theme in this conference, or at least an overriding theme, we'll be talking about some additive problems. So given a finite set A of integers, let's define the sum set. It's basically all the pairwise sums which come from A. And trivially, the size of the sum set, well, if you start with, let's say, x many elements, you get at least x many pairwise sums, and at most you can get x squared many uh, distinct pairwise sums. And often, like at least the main problem in additive combinatorics that we care about is when is this lower bound roughly sharp? So if I give you some parameter k, which finite sets of integers satisfy the fact that their sum set is at most k times a. The ratio between the size of the sum set and the size of your original set, we call this the doubling. So I want to study which sets have doubling at most k. So before we try to classify which sets have doubling at most k, it's at least good to look at some examples. And the classic examples we have are what are known as higher dimensional arithmetic progressions. So you can think of this as some sort of a d-dimensional box which has been like projected into the integers. So given some positive integer d, I basically look at some intervals of length L1, L2 up to LD, and I just look at their sum set. So I guess in the last talk, we looked at some Hilbert cubes. These are exactly like those are exactly like very nice examples of d-dimensional progressions. Here I'm allowed to take the length of my individual intervals to be much larger. So the nice thing about these generalized APs is that if my generalized AP has dimension D, then its doubling grows at most exponentially in D. So if I have a set of this form and I look at the sum set, it's at most 2 to the power D times the size of the original set. So this is a very reasonable example. If I want doubling to be 2 to the power D, I can look at any D-dimensional progression. And moreover, another example that we'd have to care about is if we have a d-dimensional progression and I take a dense subset of this progression. So maybe let's say I take 1 over c fraction of this progression in whichever way I like, where c is some constant that you like. Then indeed the size of the sum set of this dense set is at most the size of the sum set of the progression, which we know grows like 2 to the power d times the progression. And now I know since my set is dense, I lose an extra factor of c. But now we see that the doubling of a is at most 2 to the power d times c. So it depends on the dimension of the ambient progression I'm in and my density. Um, and this absolutely epic theorem in additive combinatorics, when I first started learning about additive combinatorics, I was just surprised something like this is true. It turns out that this result of Freiman from, I think, 1970s states that those are essentially the only examples. So take any finite set of integers whose doubling is at most k, so k is some parameter which is at least 1. For this parameter k, you can find some parameters d and c which just depend on k. So they're bounded above by some constant that depends on k. This is the Vinogradov notation, which has come up a couple of times in this conference. So this is just some hiding some positive constant that depends on k. Such that you have a progression p of dimension d, such that the progression P contains A. So A lies in some ambient progression, and the size of this progression is not too big in terms of A. So it depends on this constant C. And again, the dimension D also depends on this constant. So everything is fine. The dimension is controlled, and the relative density of A in P is controlled. So this is quite a nice theorem. And we care about how, like, I think essentially one of the biggest questions in additive combinatorics has been how well can we understand this dependence, roughly speaking. So in particular, due to some trivial counterexamples, you can't do anything better than d less than k here. So as I've stated, I could never prove something like d is bounded above by square root k. So assuming we can get this, which by the way we can, I think these are some classical results of Chang. Um, Assuming that this actually works, we get that if I am a set A contained in a progression P satisfying these structural estimates, then just from knowing that I'm so dense in this progression, I can show that A plus A is at most 2 to the power D times P. P is at most C times A, so I get C times A, and 2 to the power D, well, D, let's say, sort of grows linearly in K, so this is some exponential of order K. So okay, what's the point here? Why am I doing this? So I started with the hypothesis that my subset, my doubling is K. I got some structural conclusion. And if I very trivially use this structural conclusion, then I can show that my doubling is at most exponentially bounded in K. That's the nice thing about Feynman's theorem. You start with a hypothesis that your doubling is at most K, and you end up with a conclusion where your doubling trivially must be bounded in terms of K. So I guess quantitatively, we now care about how small can we make this? How efficient can this sort of circle of ideas become? So I guess sort of the biggest conjecture here is the polynomial Feynman-Ruja conjecture over integers, which sort of states that if A plus A is less than Ka, you can actually decrease the dimension of this progression by slightly going from GAP to what is known as a convex progression. So if you're happy to sort of modify the kind of structures you're looking at, then you can indeed show that the dimension is bounded quite efficiently. And now you maybe don't want to cover your entire set, but you want to cover a large subset of your set. So I want to find a convex progression P with bounded dimension, so that a lot like I have a large subset of my set A, which is in this progression, and the progression is not too big. So this is still a conjecture. I think we are like quantitatively, we've got estimates that are quite close to something like this, but still not exactly it. And somehow this threshold, like you really need to hit this polynomial, this logarithmic threshold to actually start getting some cool applications. Well, I mean, I guess Feynman's theorem, as it's known, also has really nice applications. So assuming this PFR, let me write this large subset that I just got, which is contained in this progression. Let me call this A prime. I can do the same exercise. So I can see that A prime plus A prime in particular is bounded by the size, the subset of the progression, which roughly grows exponentially in the dimension. And since the dimension is log K, this tells me that this size of the sum set is at most some polynomial in K times the size of my set. So now I started with a hypothesis that A plus A is less than Ka. And as a structural conclusion, I get that a large subset of my set has doubling at most K to the power 100, let's say. This is still conjectural, by the way. I'm assuming polynomial Feynman-Ruja. We don't actually know that this is, we don't know this unconditionally. And in particular, this is quite nice. So already for applications such as, say, proving Bourgain-Chang type estimates, sum product estimates over C, this is already enough. This polynomial loss is good enough for us to do a lot of applications. But from some sort of a purist point of view, it could be very pleasant to have a Feynman type theorem which says if I start with my doubling bounded by K, I can find a large subset, maybe not as large as what PFR gives me, but I can find a large subset whose doubling is pretty much exactly K. So I start with a doubling K, I get some structural information about my large subset, and just by trivially using the structural information, I get that my doubling of my new set is at most K. It would be very nice to have something like this. And this was a question by Ben Green on his very nice list of open problems. And Ben asked this for differences instead of sums, but you can sort of think about this for sums as well. So Ben's precise question is, again, if my difference set doesn't grow too quickly, can I find a large subset whose difference set also doesn't grow too quickly for some obvious reasons? By obviously, I mean exactly something like the structural information. So to get some sort of an idea as to how to get something like this, or what kind of a result should I expect, let me just take a very simple setting. Let me assume k is smaller than 3. So instead of working with large k, let me just work with k equals 3 and see what I can do. In this case, there's a very famous theorem of Feynman called Feynman's 3k minus 3 theorem. I think this was mentioned 2 talks ago. So let me write an asymptotic version of this. So if you start with some delta, which is between 0 and 1, and you know that the doubling of your set is at most 2 plus delta, then you can find a one-dimensional progression P. Like now you see my dimension D is precisely controlled. It's not bounded above by some arbitrary big constant. It's actually 1. And my progression P is not too big. It's at most 1 plus delta times A. So here I'm assuming size of A is large enough in terms of delta. But this is exactly the kind of conclusion that satisfies what Ben had in mind, because indeed, if I just now use the structural information that my set is, if I forget everything that I know about the doubling and just use the structural information that I'm contained in a one-dimensional progression, which is not too big, then I can just do the previous computation just from the structural information. I can see that my set has doubling at most 2 plus 2 delta. So I start with the hypothesis that my doubling is 2 plus delta. I get some structural information, which potentially can be quite lossy, but it actually turns out it's not lossy at all. So the structural information trivially gives us that our doubling is at most 2 plus 2 delta. So if delta is small, you can sort of see that we are in a regime where we can answer this question of Ben. We start with doubling 2 plus delta, and we get 2 plus 2 delta. So this is sort of okay. We can sort of answer Ben's question when delta is quite small. But already if the doubling is 2 plus half, even Feynman's 3k minus 3 theorem does not seem to give an answer to Ben's question. And I think one reason that is because you're asking for structure on the entirety of A, while Ben's question, we are happy to pass to a subset. So in particular, now let's go to somewhere around 2010. So in a very, very famous paper, Ben Green, Sean Eberhard, and Freddie Manners resolved the Erdős sum set conjecture, Erdős sum free set conjecture. And a key result that they needed to prove in this direction is exactly an answer to Ben's question for k being close to 4. So if you have a set of integers whose doubling is at most 4, like just a tiny bit below 4, then in fact, you can find a one-dimensional progression which is quite large, on which my set has density at least half. So let's unpack this for a second. So A intersection P is at least half of P, and P is large enough in terms of A. So if I think of my subset A prime being A intersection P, I know that A prime is large. A prime is bounded below by some constant that depends on epsilon times A. Moreover, just by using this information that A prime is contained in this progression with density half plus something, I can show that the doubling of A prime plus A prime just trivially satisfies 4 minus some constant times epsilon. So this is like, for me, this was really cool. Like you start with your doubling being 4 minus epsilon, you find a large subset A prime, which for very trivial structural reasons, the fact that it has density half on a progression satisfies that its doubling is at most 4. So this is kind of optimal. So we have an answer to Ben's question. Okay, I guess this is for some sets, but they also prove it for differences. So I think pretty much everything that I talk about today works equally well if you replace the sum set with the difference set. So for the purposes of this talk, subtraction and addition is the same. That's not always true, but for our purposes, it is okay. So this result gives an answer to Ben's question when the parameter k, so this was Ben's question, you can do this if k is strictly smaller than 4. And the main result I want to talk about today is doing this, going beyond 4. So going from strictly below 4 to something strictly larger than 4. So here's the main result. Suppose you have some small parameters, epsilon prime and delta. Then if your doubling is at most 4 plus delta, here delta is generally something that's a small positive real number, then either there exists a one-dimensional progression, which is quite large, and your density in this progression is at least, think about this as if your doubling is at most 4.1, then there exists a large progression, large one-dimensional progression, on which your density is at most 0.4999 or something. Like it's quite close to, it's just a bit below half. Or there exists a two-dimensional progression, which is large, and you pretty much, on this progression, your density is 99%. So you pretty much occupy most of this two-dimensional progression. So this is kind of nice, at least from my perspective. So going from doubling slightly below 4 to just above 4, you end up picking this two-dimensional structure. So already qualitatively, we have to do something beyond what Ben, Sean, and Freddie did. And it's optimal. So essentially, these two are the only things you expect. So in particular, if you have a one-dimensional progression and some subset of this progression which has density close to half, then indeed its doubling will be at most 4 plus something small. And similarly, if you have a two-dimensional progression and you have a subset of it which is pretty much most of the progression, then this subset will have doubling at most 4 plus something small as well. So another way to see our theorem is if you have a set of integers which has doubling at most 4.01, then the two obvious examples are essentially the only things that can happen. So this is kind of optimal. If there are any questions in the about the statement of this theorem, I'm happy to answer them, or I can start talking about a very high level proof strategy. So I'll just wait 10-15 seconds if anyone has questions about the statement.
So go ahead.
Okay, so I guess seeing no questions, I can't see the chat. Okay, so the statement we want to prove is if you have a set of integers with doubling at most 4.01, I somehow need to find a large one-dimensional progression on which my density is just a bit smaller than half, so like 49%, or there exists a two-dimensional progression on which my density is 99%. So here's a high-level idea. So from mid-2000s, there have been some very nice results of Ben Green and Emre Ruja, which are about rectification, saying that if your subset is small, then there is some sort of a Feynman homomorphism, isomorphism that they can construct from your set to, let's say, 1 up to n, such that the image of your set is dense in 1 up to n. So using some ideas along these lines and some Bogoliubov type ideas of Lev, we can basically go from dealing with an arbitrary set to a set that is dense in some interval. So I can assume that my set has density 1 over 10 billion in some interval, and I can try to prove my theorem for this specific case. The reason why having positive density in 1 up to n is helpful is because now I can apply Fourier analytic methods. In particular, I can apply the regularity lemma. So okay, this is an online talk. If you haven't seen the regularity lemma before, it can be quite intimidating. So here's a very, like some sort of a, obviously I'm lying here a lot, but here's a toy version of what you should think of the regularity lemma as. So you are in 1 up to n, what you basically do is you partition 1 up to n into certain blocks of intervals. You partition 1 up to n into, let's say, m intervals. M you should think of as some sort of a large constant, but it's a constant. So n is growing, m is just some large constant. And on each of these intervals, your indicator function essentially behaves randomly or pseudo-randomly. It behaves like some sort of a Lipschitz function, which is defined on the torus. So if you're in this interval, you pick some n, you look at the image of n via this homomorphism to the d-dimensional torus, and it sort of behaves like a Lipschitz function. And because this theta is sort of mildly irrational, as n varies, this sort of captures some pseudo-random behavior. Um, so you can essentially approximate your indicator function of your set with these nice Lipschitz functions defined on these very nice blocks of intervals. Okay, so assume you can do this. Obviously, I'm lying here quite a bit, but this is sort of the model case that you should keep in mind. And now you can use equidistribution. So, okay, I want to study A plus A. Yes, I want to show that A plus A is large. So what I'm going to do is I'm going to pick one such interval. I'm going to pick one such block. And I just want to show that A plus A in this block is quite large. So how do I capture A plus A? A plus A is basically the support of the convolution 1A star 1A. So if I just show that, in fact, not only if I just look at all the elements n in this block pi plus j, says that this convolution is not only positive, it's quite large. In particular, this thing, this set is contained in A plus A. So if I just show that this convolution is large in this block, I'm good to go. So again, you have some block, you have some interval. I'm looking at uh, I'm looking at more like an analytic version of the sum set. This is often called the popular sum set. So if I look at the popular sum set in this block, this entire setting allows me to show that in order to show that my sum set is large on this block, it suffices to just forget everything and move to this d-dimensional torus and show that in the d-dimensional torus, if I look at this convolution, so I had Lipschitz functions fi and fj, then the popular sums, which are controlled by this convolution, are quite large. So eventually I want to show that either A plus A has at least size 4 plus delta, or A has a lot of structure. So in order to lower bound A plus A, I can basically look at this torus and look at all possible convolutions of the form F1 star F3, F2 star F10, and show that, in fact, if a lot of these convolutions are quite nicely spread out, quite large, then I can show that A plus A is large. So, okay, if you're sort of feeling a bit lost by now, that's completely understandable. So you should think about this. So remember, 1 up to n, we break them into blocks. On each of these blocks, my set has some density alpha j, and this is captured by some function fj, which is defined on the torus. And my aim after doing all of these, using all of these nice ideas, is show that for any I comma j, so for any two such blocks you pick, either my convolution expands a bit more than I expected. So alpha a plus alpha j is sort of what you'd expect. But in fact, I expand a tiny bit more. My convolution is a bit more spread out than I thought. So this is the expansion case. This delta is exactly which will give me, this delta is exactly the thing that appears in 4 plus delta. Or there exists some I such that alpha I is just too big. It's at least half. Remember, alpha I is exactly the density of A on this progression. So if this is a conclusion that I get hit with, I'm already really good to go. Like, I know on the progression PI, my density is at least half minus something small. Or finally, and this is sort of like the hardest case, this is exactly where, so I have my expansion conclusion, I have my one-dimensional conclusion, and I still need my two-dimensional conclusion. So it says there exists some I, so there exists some such block on which this Lipschitz function that I had, which was potentially, well, I mean, okay, it was Lipschitz and nice, but in fact, it's not only a nice Lipschitz function, it's secretly the characteristic function of some Bohr set. So there is some nice homomorphism phi from the torus to from the d-dimensional torus to the one-dimensional torus. There is some interval I in the torus, and my Lipschitz function essentially behaves like the characteristic function of this Bohr set. Okay, so I have 2 minutes. I don't want to go into too many details. So maybe let me just take, let's say, the last 1 minute to convince you that this is exactly what I need. So remember, 1A roughly looks like, so if you pick this block PI, on this block, 1A roughly looks like Fi of n theta. If Fi was secretly the characteristic function of some inverse image of some interval, what am I saying? I want this n dot theta, if I hit it with phi, if I hit it with this phi phi of n dot theta should lie in some interval. So phi is a homomorphism from TD to T. So in particular, I want n dot phi of theta to lie in some interval. And if I think of phi of theta as theta prime, I want n dot theta prime to lie in some interval. And this is exactly a Bohr set condition. So this conclusion is roughly saying that I'm obtaining some sort of a two-dimensional structure on my set. I'm showing that my set has density 1 minus little o 1 on some Bohr set. And using this Bohr set, I can show that I have 99% density on a two-dimensional progression. Okay. And then maybe the last 10 seconds, let me just show. This is the hardest part. Like part 3 is just ridiculously technical and annoying. Like most of the novelty of our paper is essentially contained in analyzing this. So we require ideas from convex geometry, geometry of numbers, about properties of pseudo-random functions on the torus and in 1 up to n to basically deal with this. I had some extra slides, but I'm going to skip them. Thank you so much for listening.
Thank you very much. Are there any questions for our speaker? Hearing none, I thank Akshat again. Our next talk will be in 5 minutes.